All right, finally. So I actually made a little last minute change on this. This is not helium. I opted to go instead for argon, a reason which I will explain a little bit later, but basically it has to do with the density of the gas, but we'll go into more about the gases later. By the way, I don't know where you get argon, but apparently it comes from unicorn farts, because this freaking can was like 150 bucks, but hopefully this will solve it. This came with a certificate of purity. It is 99.99998% pure. So this should definitely solve our issues with concern about contamination, and we can proceed with our noble experiment. Ha! Get it? So what we're going to do in this video is, of course, our big experiment. But what I want to do is first address a couple of things. First of all, it turns out that I guess everybody is a chemist, and everybody is telling me about these gases that I should use. Why don't I use this gas? Why not that one? I have very specific reasons, which again, I didn't want to go into the chemistry, but I'll go into that a little bit to quell everybody's concerns about why I'm not using a recommended gas that other people think might be better. And the other thing is a lot of people, actually a whole lot of people, are really struggling with this concept of the dilution and concentration change. And a lot of people are complaining that I'm not going to change the amount of hydrocarbon and oxygen that's present in the exhaust. And that's correct, I'm not, but it's because people don't understand this concept. So we're going to go, and I promise you, I am going to make it crystal clear to you. I've thought really long and hard about a very good way of explaining this simply, which is my gift. And it'll be very clear to you exactly what we're doing. So if you're familiar with all this and you get it and everything, then you can go ahead and jump ahead to the experiment. But if you're still not clear on this and everything, then it's going to become very clear. Let's start off with some of the questions on the gases. The thing with the gas, it has to most importantly have the attributes of being inert, non-reactive, non-combustible, non-flammable. They cannot react with any of the components in the exhaust. They most importantly cannot react with the oxygen sensor. It cannot be detected by the O2 sensor. Therefore, we need a noble gas, and that would be any of these gases along this line here. And that would be the reason being because those are the noble gases. Those gases are going to be inert, non-reactive. They do not burn. They will not react with anything in this exhaust for sure. Now, a lot of people have made recommendations of other non-exhaust gases. The most common, nitrogen. Why can't we use nitrogen? Well, first of all, nitrogen is not completely non-reactive. It is definitely fairly non-reactive, but it becomes reactive at high temperatures, unlike noble gas, at least at the exhaust temperatures. So it disqualifies it. It may have some reactivity in the higher temperatures. And the second thing is that it's not true that nitrogen is not a component of exhaust. Nitrogen oxides are an example of an exhaust component. Again, not that it would have anything to do with this experiment, but if we use any component in the exhaust, people are going to complain that that is going to have some effect. Now, the other thing, there are gases in the exhaust that would work. CO2 would work fine, but of course I don't use CO2 because it is a component in the exhaust. People would freak out about it. And the other thing is that everybody's a chemist, so people are going to look and go, well, CO2, it has O2. That's oxygen. That would be detected. And it doesn't work that way, but I just avoided CO2 just simply to make it simpler for people that aren't chemists. I understand that the vast majority of you guys have probably never seen a periodic table of the elements before. So I want to simplify that so that people don't get confused with the chemistry. I don't want to go into the chemistry too much with this. So the other thing with the argon is I explained the density a little bit better to make sure we get mixed. Helium being extremely light, there may be a very good argument for either side that, well, you didn't represent our side properly because the helium didn't enter the exhaust because it's so light. That won't be a concern with the argon. So that hopefully explains a little bit with the gases. What we're going to do now is I'm going to go through this dilution thing. It will become crystal clear to you, I promise. So let's make sure you understand that, because as one viewer pointed out in my favorite comment of the hundreds that we got so far, he said something to the effect of, wow, there's really a degree of beauty to all of this. And that's actually true. And if you don't understand what's happening here, you're not only missing the experiment, but there is a beauty here that you're missing, and I really would like you to see it. So let's go ahead and explain that. All right, my apologies for you guys that already get it and you understand this and everything, but the truth is you guys are in the minority. Most people are struggling, and I think it's really important that they understand this concept here, because otherwise the experimental design doesn't make sense, and we're going to get billions of questions that are illogical or irrational because people don't understand this critical concept. So what we've got here is our gases that we're going to use. They will be color coded. AR, of course, will be argon when we get there. And we've got our exhaust pipe here, and we've of course got our oxygen sensor. And that, of course, would be the pre-cat oxygen sensor, your oxygen sensor that gives you your waveform like that. And of course, in the exhaust, we are going to have some of the unburned oxygen in there and some of the unburned hydrocarbons, some of the unburned fuel in there. And what we're going to do is assume, because this isn't actually how it is, but just to make the math easier, we're going to assume that at stoichiometry, we would have an equal amount, an equal proportion of hydrocarbon to oxygen. So 5 oxygen molecules to 5 hydrocarbon molecules, 1 to 1. And that would be to create stoichiometry and give our oxygen sensor trace. Now, of course, some of you are like, well, no, the trace is because we go a little bit rich and a little bit lean and a little bit rich. We're going to just ignore that for now to make it simple. You know, I guess I could put 0.45 volts and a flat line across or something, but we want to keep this consistent with what people understand. So we're just going to assume that a 1-to-1 proportion of oxygen to hydrocarbon gives us our stoichiometric trace. Now, let's do this. This is the most important thing. This is where I need you to really use your imagination. I want you to think of this oxygen sensor as it's like an eyedropper, like a medicine dropper. So what we're going to do is we're going to squeeze the bulb on the medicine dropper, stick it in the exhaust, and we're just going to release it and suck up a little sample. Of course, we don't suck up the whole exhaust, but we suck up a little sample from the exhaust. What's that going to look like in our tester? Well, we're going to bring up an equal proportion of hydrocarbon to oxygen because it represents our concentration in the exhaust. So we would get a little sample here, and of course the oxygen sensor looks at that sample. It knows we're still in stoich. So we're really happy here. That's great. Now, the question is, does it do this because it's reading the oxygen, or does it do it because it's reading the hydrocarbon? That's where the question is. So let's do this. Let's make a variable here. Let's go ahead and let's say we cause a vacuum leak. So now we've added considerably more oxygen, and this, of course, when we do our eyedropper test, is going to change our sample. Now when we do our eyedrop test and we squeeze our eyedropper and we take a little sample of the exhaust, what's going to happen? What is our sample going to look like? Well, it's going to be very different. First of all, we're going to pick up less hydrocarbon than we did before because it's going to be less likely to pick up a molecule. We are definitely going to pick up quite a bit more oxygen than before. And as we know, with extra oxygen in the exhaust, the O2 sensor is going to start reading lean. Now, the question is, how does it determine this change? How does it know it's reading lean? Well, one argument, mine, and I come to understand most of yours, is that it detects the additional oxygen that was not present before. And when it sees this additional oxygen, it is an oxygen sensor. It measures the oxygen, it sees the increase, it goes lean. Now, the counter argument to this is that no. See, the hydrocarbon content changed. It measures hydrocarbon. When it saw there was less hydrocarbon than there was before, it detects a lean condition. As you can see, both arguments are supported. Now, we're back at stoich. And hopefully you can see that the opposite would be true if we were to increase the unburned fuel. Maybe we have a leaking fuel injector or something like that, that we would see the opposite effect. Let's just go ahead and show that just to make it simple. So we increase the amount of hydrocarbon in there. Both sides agree this is going to cause it to go rich. So what happened? Well, remember our baseline was we measured that. So that's our baseline measurement. But then we introduce more fuel into the exhaust. So what does our sample look like? Well, it's because we've got a lot less oxygen, we're going to pick up less oxygen, but quite a bit more hydrocarbon. Okay? The oxygen sensor is going to go rich. Did it go rich? Because the oxygen sensor detected less oxygen than there was prior to the event, or did it go rich because it's a hydrocarbon sensor and it detects more hydrocarbon present? It knows the condition's rich. Both sides have their argument. Okay, so we're back at stoich, and now we're going to make it a little bit interesting because we're going to put propane into the mix. And we go ahead and we add some propane in there. And of course, we know that if we add propane into the mix, both sides of the argument agree we're going to go rich. And why is that? Well, it's because propane is a hydrocarbon. It's really no different than the unburned fuel, the unburned gasoline. They're both hydrocarbons. So we're still doing the same thing as if we had a leaking injector or something, and we're adding more fuel into the system. So again, the argument is the same. When we take our sampling, when we introduce the propane, it's going to look something like this. And now when we compare it to baseline, we have an argument here. Did it go rich because, again, we detected less oxygen? It's an oxygen sensor. The propane made it so that we detect less oxygen. Or is it, again, a fuel sensor? And because propane can be detected by the oxygen sensor, it detects more hydrocarbon than before, and therefore it's a richer condition. So the propane doesn't help either side. We still support either side. Each side is claiming that the thing we're diluting with is measured by the oxygen sensor. You can see where it's critical that if we're going to solve this argument, we cannot use something that is detected by the oxygen sensor. It cannot have oxygen, it cannot have hydrocarbon or anything. And that is the reason why whoever the person was that suggested I use acetylene needs to be punched in the throat, because you're not understanding this, and you should go back to watching videos with people who just change alternators and radiators, because we cannot do that. We have to use something that is not going to react with either of these chemicals, the oxygen or the hydrocarbon, and it also cannot be measured by the oxygen sensor. Introduce my idea. Okay, we are back in stoichiometry, and here is the beauty of the idea. This is why this is a scientific experiment. This is where it works, okay? What I am doing is I am going to introduce argon. I'm going to introduce it directly into the exhaust stream. That is going to add argon molecules in here. Remember, the argon is not going to react with the oxygen. It is not going to react with the hydrocarbon. It is not detected by the oxygen sensor. Argon is completely inert, non-reactive. It is a ghost, but it's a ghost that takes up space. Now, let's go ahead and do our eyedropper test. We take a sample. What is it going to look like? It is going to look like this. Both the hydrocarbon and the oxygen are going to be reduced. So when the oxygen sensor detects the change, it is going to have to react either rich or lean based on this. That reaction tells us which gas it must have detected. If it is an oxygen sensor, then it's going to compare to the baseline before I added the argon. It is going to see less oxygen. If it sees less oxygen, it's going to go rich. But if it is a hydrocarbon sensor, then it is going to look at the hydrocarbon, see that it was less than before baseline. It is going to determine less hydrocarbon. It is going to go lean. So that is why I have to use a inert noble gas, and that is why even though it is not changing the actual amount of hydrogen, hydrocarbon, and oxygen in the exhaust, even though that remains the same, because it does, the dilution effect causes our sample to be affected. Hopefully that makes it crystal clear to you, and this way the oxygen sensor is forced to make its decision, rich or lean, and we will be able to determine how it did that detection. Oh, and one other thing I forgot, because when you're scientific, you have to take into account all possibilities, Your other possibility here is, of course, that the O2 sensor trace does not change. Now, I don't see that happening, but if that happens, the only explanation would be that it is measuring basically the ratio. It's sort of like an air-fuel ratio, and it at least, if it doesn't measure the ratio, it requires one to measure the other. And in that event, as far as I'm concerned, that basically, kind of says both sides are right. I do not see that as being the thing. I do believe we're going to see that it is an oxygen sensor, and it's strictly going to react to the lower oxygen, but we'll see. All right, as you can clearly see, that explanation was truly brilliant, as is the experimental design plan. So hopefully now you understand exactly what's going on and why this works, and I won't have to answer all these chemistry questions anymore. I'm going to leave it up to you to understand that concept, but that is the concept that this whole experiment is based on. So we are going to go ahead, and I'm just going to set up the car here and get our oxygen sensors warmed up and all that, and you guys are free to go ahead and take a beverage break or something in the meantime. Molecules detected, the O2 sensor.
Blah, blah, blah. All this guy ever does is just talk. Never even fixes a car. Scotty would have replaced O2 sensor in 2 minutes. Oh, God! That's way too much cock for me. Ugh. Ugh. Oh, that's better. But hey, there's still the same amount in the cup. Can someone explain that to me?
I know, but I think it's important to get to know the people that give thumbs down on my videos, especially this one. So what we've got here is our actual, pretty much same setup as before, except my hosing line here is going to go directly through the secondary air to, actually this will be the bank 2, I'm pretty sure. So our bank 2 exhaust, so we're going directly to the exhaust manifold with this one ahead of the oxygen sensor, obviously. And I've got a little clamp here to prevent contamination from room air between changes of the cylinders. We've got our cylinder, of course, here with our argon, and I've got a propane cylinder here. I've got shop air somewhere around here. The first thing we have to do, again, it's eager to get exciting, but remember, we do not have an experiment if I just go ahead and pump argon into here. We have to establish that the sensor is capable of detecting both rich and lean. Otherwise, we don't have controls for the experiment. So we have to assess that the oxygen sensor can detect both directions so that no side can say, well, you never showed the oxygen sensor can't detect lean or rich. So I'm going to go ahead, start up the car. I've already got it warmed up a little bit. We'll go ahead and we'll pump room air first, and we'll make sure that the O2 sensor reacts lean. Okay, obviously our oxygen sensor is going good there, but I want to do one other thing. I want to go ahead and let's bring up a table here, and I want to show the long-term fuel trim on the bank is good so that there's no argument that we don't have any abnormal condition with the car or something like that. Okay, long-term fuel trim bank 2, and we can see that it is 0.8%. By the way, evidence of that idle air control motor fix from a few months back. So we have a good, healthy looking car here. I guess I'll go ahead and bring up the short-term fuel trim as well, just to make it easier for people that are familiar with that. Okay, all of those should easily be in the shot. Let me fix the glare for you guys a little bit. Okay, the first thing I'm going to do is just add a little bit of oxygen into here. We of course should see our system go lean. So let's go ahead and verify that. And you can see that we go lean. So that's good. Okay, let's go ahead and stabilize now. Okay, looks like we're stabilized here. So now we can go ahead and do our propane. And oops, I let go of the hose a little bit there. That might put a little air in there. Let's make sure we're stable. And it looks like we're good. So I want to make sure I add enough here that we don't get compensation by the fuel trim for it. So we want to stay rich long enough to confirm. And that's just me blowing in some more room air. There is our rich. So we can see that we've got good oxygen sensor response. And that right there is because we had some room air still trapped in the hose before the clamp. Okay, you can hear the engine stumbling from the overly rich conditions. So let's give it a minute or two. Look how negative we went. Let's go ahead and give it a minute or two here to stabilize, and then it's the moment of truth. Okay, looks like we're stabilized again. So let's go ahead and I don't have a regulator on here, so I'll have to feel a little bit. Whoa, that's a lot. Okay, we got some argon flowing. So we're stabilized. I've got a good flow of argon, and let's go ahead. And that's just room air going in there, so don't panic, but let's see what we get. We actually do not seem to have change. And there is a good amount of argon going in there. Almost as if you need both hydrocarbon and oxygen is pretty much what my conclusion is about to be here. But let's try that one more time. Add our argon. And that's going in. And I'm adding a fairly healthy amount. And it does not look like we're getting a change still. That is just amazing. And wow, that's it. That's all of our argon. We are out of argon now. So I was not able to get it to go either rich or lean. You know, what I'm gonna call this is that you need both. I'm gonna say you have to have both oxygen and hydrocarbon on this thing. And that appears to be the best explanation. So let's talk about it. Okay, that did not nearly go with the result that I had expected, but I do want to show you this one thing. Steve Robb, one of the regular contributors to the channel. Okay, and we can see from Steve Robb's explanation here, although I'm not sure I agree with the logic, but he's saying that there's going to be no change at all because the O2 sensor is so sensitive to even the lowest levels of oxygen. And of course, remember, we have to also consider the potential for its detection with hydrocarbon there, but he does not think there is going to be a change. And my response, of course, is that it's not possible unless the O2 sensor is an air-fuel ratio sensor. Otherwise, it's going to have to go rich or lean. So in other words, the sensitivity doesn't matter. In the traditional thinking, the sensitivity is even better. The more sensitivity, the better. I could flood the thing because I'm minimizing the amount of oxygen and hydrocarbon that would be detectable. And of course, remember, the engine's not dying because I'm not putting that in through the intake. That's why the engine didn't stumble or die or anything. I'm just affecting the detection. Because the proportion of oxygen and hydrocarbon stayed the same, even if it was minuscule amounts in our sample, the proportion is still the same. The oxygen sensor clearly did not detect any difference. Or it's possible that, another thing is that I could have flooded out everything and the oxygen sensor doesn't detect anything, but that clearly wasn't the case. I put in everything from a very small trickle to enough that I was expecting the hoses to blow off. But it's very clear in my estimation here that you have to have both. You need both hydrocarbon and oxygen for this detection to work, and it is the proportion. It clearly has some measurement with both of them. So I guess I'll have to do some more reading up on it, but this to me verifies that, in my opinion, both sides are right. I don't think you can do one without the other. I think it needs both. So fascinating. You know what though? I do want to do one thing that I'm kind of curious about. And that is, of course, I still have a score to settle with this bitch. So as we know, I was suspecting that the cause of the lean condition was because there's obviously air contamination in this thing, and a pretty significant amount of it. And we're just going to go ahead and verify that. Again, these are both noble gases, so it's not like helium's going to react and argon isn't. It's not like that at all. They're both noble gases. So let's go ahead and first of all, let's just verify that we've still got our response here. And you see we do. We go lean. Okay, if there is a lean condition with this, it is because there is oxygen. Okay, there it goes. And it looks like it went lean for a second there. And actually, look at that. It does not go lean. This is pure helium. It's no different. Wow, it's no different than the argon was. So I was wrong about the effects of entering it into the intake manifold, clearly. This actually, again, supports the argument that you need both. But there is clearly no oxygen in this. The one guy, I'm going to take his name down because he was right. This stuff is clearly as pure as the argon. Amazing. I guess that didn't go as anybody expected, but clearly I was wrong. It makes a big difference. Putting into the intake, there were some people, and I apologize because I was certain that it didn't make a difference going through the intake and admittedly diluting the air. I now see the error in my thinking with that. I was definitely mistaken about that. But the one thing that I'm definitely sure, the one thing I have no question about is that the idea worked. There's no question in my mind whatsoever that this idea worked. We basically have the same proportion detected by the oxygen sensor in much, much lower amounts. And I'm convinced at one point when I pretty much decided to empty the tank that we probably were detecting very few molecules, but there's no question in my mind the proportion is even, and the reason we got no change is you have to have both. There's no doubt in my mind about that. So unless somebody can come up with a better explanation, but that is clearly it. And I was also very surprised to find that balloon helium is actually, at least as you know, it's got to be about 99% pure. It was not, after all, air contamination. So that's the conclusion that I'm going to have to draw from this. There's no other explanation that I can think, and you know, this is a pretty good lesson in the way science goes. We had three possibilities: lean, rich, no change. In my opinion, the no change was not an option. I believed it was going to be either an oxygen or an HC sensor. There is no question you need both. It may be arguable that it's an oxygen sensor, but it needs the presence of hydrocarbon to measure the, as far as I'm concerned, that doesn't matter. It doesn't matter. Either way, you have to have both. It doesn't measure just one or the other. You've got to have both. So that's the end of this video, I guess. I'm still kind of whizzed about that, especially since it cost me like $200 to do this. But at least I can make a lot of party balloons. So anyway, thanks for watching. I hope you found this helpful. Definitely looking forward to the comments on this one. We'll see you later.